Hey everyone, today we're going to crack open your computer, metaphorically of course, and really get into a revolution in how it thinks. We're going to look at this hidden battle between two completely different ways of processing information. And trust me, by the end of this, you'll look at your own machine in a whole new way. Let's get right into it. So let's start with a puzzle. You've got this super powerful CPU, your central processing unit. It's a genius, right? A master of complex logic. But try to get it to render a modern video game, and it just falls apart. Meanwhile, the GPU, the graphics processing unit, handles those same stunning visuals like it's nothing. So what gives? The answer is all about how they work, and it's a total game changer. To really get this revolution, we have to go back to the very beginning. Back to the classic way computers have pretty much always done things. Think of it as the original blueprint. One single, hyper-focused mind working on one single task at a time. Now, this classic model has a name. It's called SISD, which is short for single instruction, single data. And, the name really gives it away. It's exactly what it sounds like. A processor grabs one instruction, applies it to one piece of data, gets an answer, and then, and only then, it moves on to the next thing. This is the bedrock of pretty much every CPU out there. The whole process is this really clean, really linear four-step dance. First, it fetches an instruction, something like add these two numbers. Next, it fetches the data, the actual numbers you're adding. Then it executes the instruction, does the math. And finally, it stores the results somewhere. It's methodical, it's precise, and for a really long time, it was all we ever needed. Probably the best way to picture SSID is to think of a lone master craftsman, maybe a watchmaker. This person is an absolute genius. They can follow incredibly complicated blueprints and do these super delicate, intricate tasks one after the other. But no matter how brilliant they are, they can only do one thing at a time. So if this lone worker model was so great, what happened? Why change it? Well, the world changed. The kinds of jobs we started giving our computers were just fundamentally different. And our meticulous lone worker, they just couldn't keep up. They hit a wall, hard. And that wall? It was basically a tsunami of data. All of a sudden, we weren't just asking our computers to do one complex thing. We were asking them to do millions, sometimes billions, of really simple things all at the same time. I mean, think about rendering a video. Every single pixel needs its color adjusted over and over for every frame. Or an AI model that needs to do the exact same little calculation on millions of data points. For a lone watchmaker, this is an absolute nightmare. It's like asking a master artist to paint 1 million fence posts one by one. So the solution wasn't to somehow make the lone worker faster. Nope. The solution was to hire an army. And this led to a completely new way of thinking called parallelism, which comes in a couple of different flavors that basically power our entire modern world. Okay, first up in our army is SIMD, that's single instruction, multiple data. And the whole idea here is just raw efficiency. Instead of one processor doing one thing, you have one single command that goes out to tons of processing units. And they all do that exact same thing on different pieces of data, all at the exact same moment. Our analogy for this one is a drill sergeant. Picture the sergeant yelling out one command. Add 5, and an entire platoon of soldiers, our processing units, instantly adds 5 to whatever number they're holding. It's perfectly synchronized, it's powerful, and it's incredibly good for those boring, repetitive tasks. But modern GPUs took this idea and pushed it even further with something called SIMT, single instruction, multiple threads. Now, this is the real magic behind the graphics card in your computer. It takes the drill sergeant's efficiency, but then adds this crucial layer of flexibility. Each soldier is now what we call a thread. It's like a lightweight, independent little worker. A single high-level command still guides them all, but each thread has a bit more freedom, allowing for thousands, even millions of them to work in parallel. So if SIMD is like a platoon of soldiers, SIMT is like a whole army of secret agents. They all get the same mission directive from headquarters, the big picture. But each agent is out in the field acting on their own piece of intelligence. They're all working in parallel on this massive scale, and it creates this amazing illusion that every single one is completely independent. Okay, so we've got the lone worker, the drill sergeant, and the army of agents. But what does this actually look like in the hardware? How do these differences really play out inside the chip? Let's break down those critical differences. This table really sums it all up. Look at the CPU, our SISD model. Its main goal is low latency, which is just a fancy way of saying finish one single complex task as fast as humanly possible. To do that, it has just a few very powerful processing units, or ALUs. Now look at the GPU. Its goal is totally different: high throughput. It wants to get the most jobs done at once, period. And it does that with thousands of simpler, less powerful ALUs. So you see, it's not about which is better. It's that they're designed for completely different things: complex logic versus massive, massive data parallelism. But this army of agents, it has a weakness, a real Achilles heel, and it's called branch divergence. So what happens when some of the agents in a group need to follow plan A, but the other agents need to follow plan B? In the super parallel world of a GPU, this creates a major traffic jam. So here's what the GPU is forced to do. When the threads disagree, like on a simple if-else statement, they can't just go their separate ways. So the hardware makes all the threads that need to follow path A go first, while every other thread in that group just sits there, waiting, doing nothing. Then, once they're done, the GPU runs path B for the rest of the threads, while the first group now has to sit and wait. All that waiting just kills the performance benefit you were getting from being parallel in the first place. So what does this all actually mean for you and your computer? Well, it means there is no single best processor. It's all about using the right tool for the right job. You absolutely need both. And this right here brings us all the way back to our original question. Why is your fancy CPU so bad at playing games? Well, the CPU, our lone worker, is perfect for running your operating system, managing databases, things that require complex decisions that happen one after another. But the GPU, our army of agents, is built from the ground up for these huge parallel tasks like AI training, scientific simulations, and yes, calculating the color of every single pixel in your favorite game. But I want to be clear, this army is not a silver bullet. Parallelism has real limits. There's something called Amdahl's law, which basically says that any task is ultimately limited by the parts that have to be done sequentially, the stuff only the lone worker can do. We've already seen how branch divergence creates those awful traffic jams. And on top of that, if you don't have enough data to keep all those thousands of threads busy, they just sit there, idle, wasting a ton of power. Oh, and for programmers, trying to find a bug in parallel code can be an absolute nightmare. It's an incredibly powerful tool for sure, but you have to use it wisely. So I'll leave you with this to think about. We live in this age of AI, of big data, of incredible graphics, a world that is tailor-made for that army of agents. But as we keep pushing further and further into massive parallelism, what are the crucial problems of the future that will still demand the focused, sequential, step-by-step logic of that one indispensable lone worker? Something to chew on. Thanks for watching.